My name is Ilya. I am one of the members of the center. I've been coming here for, I think, more than 15 years now to both summer and winter programs. And so I want to thank you for welcoming and hosting our center here in Aspen. It's a wonderful place to do physics and astrophysics, and we really benefit from this wonderful environment. So thanks very much to all of you for supporting us and, of course, for coming to this public lecture. I am also here this year as one of the organizers of a meeting on interacting binaries. So this is stars that are interacting with each other. There are all kinds of exciting interactions that can happen between stars, whether they are gamma ray bursts or supernova or gravitational wave mergers. And we're discussing all of these things over the 3 weeks of the meeting. And of course, one of the participants in this meeting is Professor Hawkins, who is going to be giving you a lecture today. We'll be telling you about galactic archaeology. I will let Keith explain what exactly that means because he's infinitely more competent than I am at this. Let me just mention a couple of words about Keith. So Keith did his undergraduate degree at Ohio University, then did his PhD at Cambridge in 2.5 years. Now, just for comparison, it took me 6 years to do my PhD. So as a sort of preparation for getting your mind working before Keith's lecture, you can figure out how many times Keith is smarter than I am based on that. After doing his PhD at Cambridge, Keith went to Columbia University as a Simons Foundation Fellow, then started a permanent position at University of Texas at Austin. And so without further ado, please come on up.
Okay, can everyone hear me? Wonderful. Good evening, everyone. I'm Keith. I'm from the University of Texas at Austin, so I'm glad not to be in Austin right now. It's upwards of 100 degrees. So the story that I'll be telling you tonight, or the talk I'll be giving, is really about our galactic home, our cosmic home, the Milky Way. And you can kind of see the Milky Way here, but I'll talk a lot more about the Milky Way over the course of this evening. And so let's start out with my nominal home, right? So the story is really about our home. I want to start with my home. So this is my home. This is the city of Austin. Beautiful. It's wonderful, except in the summer when it's 100 degrees. And so I travel, 16 hours a drive or 2.5 hour flight. You can actually fly direct to Austin from Aspen, which is great. And the public transit here is fantastic. So I just can take the public transit from the airport to Aspen Center for Physics, which is where our lecture is tonight. This is our home base for tonight. This is where we're going to start our exploration of the Milky Way galaxy. When you look up from here, our home base in Aspen, what do you see? So you're going to ask me questions, right, towards the end. So I'm going to ask you questions during. That sound fair? All right, so you look up, what do you see? Stars. Great, wonderful. You do indeed see stars. I know that this is not a middle school crowd because they usually say the ceiling, the lights. But in fact, if you go out on a dark night here in Aspen, this is actually what you would see. This is actually an image taken from Aspen. You can see the Milky Way here. This Milky Band of stars is, in fact, the Milky Way. And you can actually see probably a shooting star here, our Starlink, which is unfortunate for astronomers because they get in the way of our images. So this is our home. This is our Milky Way. And if we go to even darker skies, you go a little bit outside of Aspen. Now, in my opinion, Aspen's one of the darkest skies that I see because I live in Austin. If you go even further outside of Aspen, you'll get to Maroon Bells, which is amazing place to hike, but it's even better to see this night sky. Go out and you let your eyes dark adjust, or you take a nice image camera out there. I see something like this. This is the Milky Way galaxy from the Maroon Bells, just up the road from. And this is what I study, this galaxy here. And our galaxy is made up of stars. So each one of the points of light in this image is a star. We'll talk about what stars are and what galaxies are in a moment, but this is a star. So every point of light is a star. And then in the middle here, you've got enormous amounts of dust. So a lot of people, when they look at this image, they say, that's a dark band. There's no stars there. In fact, there are stars behind the dust. So imagine, if you will, take an old rug and shake it out, and you see an enormous amount of dust that pops up out of that rug. You can't see the person behind you, which is kind of gross. But that's what's in our galaxy, our Milky Way. You just can't see behind it. There's gas and there's cats and there's dogs and there's humans. And basically that's what creates our galaxy, the Milky Way. It's made of 100 to 200 billion stars. And our sun is just one of those stars, which is kind of an incredible number when you think about it. And as a galactic archaeologist, my job is to study Milky Way and use it as a laboratory, understand how galaxies across the universe form, assemble, and evolve over cosmic time. So this image in the background is what we would call our cosmic home. And I use stellar fossils, which I'll explain in a moment, to understand how our galaxy formed and evolved and assembled itself. So this is actually an image from the McDonald Observatory out in West Texas that I use a lot. You can see it's peppered with beautiful stars. And a star, like the sun, is nothing more than, I like to quote the Lion King here, those of you who are familiar with Pumbaa. Pumbaa actually got it more or less correct, that stars are balls of gas burning billions of miles away. Now, what Pumbaa did not get correct is that nuclear fusion is in the furnace of those stars, creating their light. Otherwise, Lion King, actually, it's one of my favorite of the Disney films, and I figured Pumbaa is one of my favorite characters, so why not put it there? So this is our nearest star. This is the sun, and the sun is a big ball of gas burning not quite billions of miles away, but millions of miles away, since it's just our closest star. And every star in the night sky is a fossil in some level for two reasons. First, if you look up at the star, like the sun, which I should probably warn you, please don't do that if you don't have protective lenses, because it will blind you. If you look up at the sun, you're not seeing the sun as it is now, you're seeing the sun as it was 8 minutes ago. It takes light 8 minutes to go from the sun's surface to our eye.
Excuse me?
Yes.
The sun is the biggest star in our galaxy.
So the sun is not quite the biggest star in our galaxy.
You should look up at night when you sleep here.
Okay.
Close.
There are tons of shooting stars, but it's not quite the biggest. It is one of the biggest in the night sky, or in the day sky rather, because it's so close to us. Okay, so why do I care about stars like the sun? It's primarily because stars like the sun are fossils of what went on in the universe billions of years ago. So I'm going to put up here all of the major areas of astrophysics and tell you why I think stars are more important than those major areas. So for me, how many people here are interested in finding life on other planets, or interested in whether there's alien life? Okay, very important question, right? I think stars are a fundamental part of answering that question. Why? Because we have a saying in astronomy. The saying goes, know thy star, know thy planet. So there are planets out there, hundreds of them, thousands of them, probably billions of them. I believe that one of them probably has alien life. But we only know the planet as well as we know star. So we have to study the star first to better understand the planets. And my group, actually at Texas, one of the areas of astrophysics that we are working on actively, something called the Galactic Habitable Zone, which is where in the galaxy life could exist. How many people are interested in stars themselves? I'm interested in stars. Yes, this is my crew. Okay, good. I'm interested in stars. Stars themselves are also incredible tracers of the Milky Way and galaxies in general, because stars make up the galaxy. So they're the basic building blocks of the galaxy. So you have to understand stars. You want to understand the galaxy. How many people are interested in other galaxies, not our own? Okay, so this is a crowd that's pretty much interested in everything, it seems. So you've got other stars and other galaxies. And remember, we call this X-gal, where you can see other galaxies, but what you're seeing in those galaxies is their stars. You have to understand stars, understand other galaxies. How many people are interested in cosmology? That is the large scale structure of the universe. I was expecting most people, so great. It turns out that in order to do cosmology, in order to understand the basic structure of the universe, we have to be able to compute the distances to those galaxies, which requires us to use stars. You kind of get the picture of where I'm going here. Stellar astrophysics and stellar astronomy, which is what I do, understand the Milky Way, is in my opinion, the fundamental area of all of astrophysics. Whether you're interested in planets or you're interested in the other side of the universe, you have to understand ours. And my group, which is pictured, and various members of my group are pictured here, work on various areas of stellar astrophysics for these particular areas of general astronomy and general astrophysics as well. So I've talked about what a star is, but I haven't necessarily defined a galaxy. Galaxy is nothing more than a collection of stars and dust and gas and humans and cats and dogs and the whole 9 yards, held together by their mutual gravitational forces. And as a galactic archaeologist, my goal is to understand how galaxies form using our galaxy, the Milky Way, as a test bed, laboratory. So for me, one of the coolest things about being an astronomer is that's my laboratory. That's what I get to do. And so that's why I love what I do. Like any good archaeologist, like Indiana Jones, which this reference was lost on Gen Zers. It turns out that they don't actually watch Indiana Jones, except for Indiana Jones movie just came out. So I hope everyone has seen it. No, I don't actually work for that film, but I am like the Indiana Jones of the galaxy, right? I study fossils in our galaxy and try to piece together how it formed. I was once at a talk, actually, and I was told that an archaeologist studies artifacts and a paleontologist studies fossils. So I should be a galactic paleontologist. I like the idea of being the Indiana Jones of the galaxy. So I'm going to keep archaeology. Like any good archaeologist, like Indiana Jones, this is the action figure, has his whip, right? That's one of his primary tools. I have my tools as a galactic archaeologist, and mine telescopes around the world. So one of the things that I get to do is I get to travel around the world, and I get to go to telescopes. These are telescopes from anywhere from California to Hawaii, where I get to spend and actually study and observe the galaxy, which is my laboratory. I get to escape the city of Austin, especially in the summer, and go to telescopes like this. So this is the McDonald Observatory out in West Texas. And this is the primary instrument that I use, actually, the 2.7 meter telescope. And this is actually where I spend quite a lot of my time, or my group does at least. And so the Milky Way, in my opinion, is my laboratory, but I use it to answer some of the key fundamental questions of our galaxy. These questions include, how do galaxies in the universe form? I think that's a big question. We don't really know the answer. How does our galaxy and its stars form? How does our galaxy assemble and evolve over time? And how is our galaxy structured? These are the key questions that drive me and drive my research program. And they kind of go in order of like their gravitas in some sense. How do galaxies form in the universe is a fundamental pillar of astronomy, and we don't know the answer to that question. Some ideas, don't quite know. And so each one of these questions going down is a slightly more specific question to start getting at the bigger question above. These are the questions that excite me. These are the questions that get me up in the morning. I don't actually like being up in the morning. I like being up at the night, obviously, because I'm an astronomer. But these are the questions that get me up and get me driving to work and going to work every day. And it's a real privilege, actually, to get to be an astronomer, to do this kind of work and answer these types of questions. And like any good scientist, the best way to answer questions is through the scientific method, which we are going to go through. Does that sound kind of middle school to you? Because when I first did this, it sounds kind of middle school, except for I taught middle school math and science in Ghana and West Africa. So maybe that's why I'm doing this. But you'd be surprised how many people and students don't know what the scientific method is or how to apply it. So tonight, we're going to go back to the basics. We're going to go to the scientific method. I'm going to walk through it, and we're going to answer some of those questions on the slide previously using the scientific method. So simulating exactly what I would do in my job as an astronomer. So the first part of the scientific method is to ask a question. It's kind of easy, right? Ask questions all the time. This is actually one of the hardest things for a professional astronomer to be able to do correctly. Asking an important question is very difficult. You need to figure out what's important to ask, what hasn't been answered before. So the question is the first part of the scientific method. Second thing we do is create a hypothesis, an idea answers that question based on what we already know. Third thing to do is experiment. And in my case, it's mostly observe the heavens, try to answer that question or try to prove that hypothesis correct or incorrect. Then we analyze the data and we then communicate our results of what we found with that observation on whether our hypothesis was right, wrong, the scientific community through publications or the public through lectures like this one. That's the process of science. That's what we do. This is our bread and butter. And it does sound middle school, but it is quite surprising to me how many people just don't really recognize how to do this and implement this in practice. We're going to practice this tonight. We're going to start with one of the questions that I had on the previous slide. How does our galaxy structured? Okay, that's the question we're going to ask. And what is the next thing to do in the scientific method? Create a hypothesis. We're going to start with two hypotheses. Oops, I head a bit too far. Hypothesis one, our galaxy is nothing more than a ball of stars, and we're sitting in the middle of that ball. That's a pretty easy idea, right? So this is our galaxy. Imagine this is our galaxy. And the Earth is that blue ball, pale blue dot, as Carl Sagan would say. And if I go and observe this, this is an idea, right? This is a hypothesis. But I have to then predict what I would see here on Earth. So if I put myself on Earth, which is, I'm not really blue. I decided to use a blue figure because the blue pale blue dot. If I put myself here on Earth and the Milky Way is nothing more than a ball of stars, the prediction is that if I look up and I see this ball of stars all around me, I'm going to see stars on this side, stars on this side, and stars on this side, stars on this side. Does that make sense? I'll just see the equal number of stars across all areas. And that's it. That's my prediction. But let's come up with another hypothesis. I have one hypothesis that we're going to test tonight. The second one is, let's say the Milky Way is a disk of stars, not a big ball. It all lies in a disk, kind of like a pancake. If it is a disk of stars and the Earth is sitting in that disk, you might see something like this. You'll see some stars that are above and below the disk, but most of the stars will be concentrated along the disk. So when I look up at the night sky, I'll see stars along a disk, concentrated in one area. That's the prediction of the second hypothesis. We'll see stars concentrated along. All right, so now we have our question. We have our hypothesis. What's the next thing we do? We observe. So let's observe. Let's make an observation from here in Aspen. Let's go back to Maroon Bells and look up at the night sky. It's a suspense. Because it actually does take time to get observations. I put a blank screen here, and specifically because I wanted to simulate the fact that astronomers also have to deal with weather. Tonight, it might be cloudy, so we might have to sit here for a while. But I'm going to speed up the process, and we're going to make the observation. Right, so here is our galaxy from Maroon Bells. Here's our observation. So my question to you is hypothesis one, ball of stars, or is hypothesis two, disk of stars, correct when you look at this image?
Yeah.
Two. One for one?
Make an argument there's something else in the way, and that the band is actually, surrounded by stars that are more distant.
Very good. Very perceptive. In fact, if I look at this, I immediately see the disk from prediction two. So hypothesis two is likely correct. But I also see stars here and here, right? Maybe hypothesis one might also be correct, that there might also be a big ball of stars surrounding the Milky Way. So this is our image. This is our observation from here in Aspen. But one thing that happens is that we can't see to the southern hemisphere, right? The Earth blocks our view. So one of the most annoying things about being an astronomer, that if I take a great image in the northern hemisphere, I still don't have the full picture. I have to then go get images in the southern hemisphere too, which is great because then I get to travel to the southern hemisphere. So let's say I go to Chile, and I love going to Chile. In fact, first time I went to Chile, I had been observing the stars in the night sky. Or I had been trying to do galactic archaeology during my PhD. At the end of my PhD, after spending years trying to understand this galaxy, I traveled down to the southern hemisphere to the Very Large Telescope because we're great at naming things. It's actually literally is called the Very Large Telescope. If we go down to the southern hemisphere to the Very Large Telescope, and that pause because it takes a while to get down there. See this. This is from the Very Large Telescope in Chile. When I saw this, I cried. I wept, actually, because you spend years studying something and then you get to see it. And it's beautiful. And let's recreate our similar scientific method in this side, right? We see a disk of stars here. Right? That's our concentrated along one sky. If you look closely enough, there is a big ball of stars in the middle. It's called the bulge. So both hypothesis 1 and hypothesis 2 are correct. And the reason why I partly did this and set it up this way is to give you an idea that while in astronomy, our goal is to falsify hypotheses, or at least that's my philosophy of science, we should be falsifying ideas. Sometimes we can come up with so many ideas, and those competing ideas can be correct multiple times. Both could be correct, not just one. So this is the anatomy of the Milky Way, or what we think it is. In real life. And this is based on observation. This image here is an artist's impression of the Milky Way based on some of those observations I just showed you. We did this kind of in practice, but I'm going to walk through a little bit of the structure of the Milky Way. So this is an artist's impression of the face down view of the Milky Way, and this is the face on view, or the edge on view rather. You see that big ball of stars here. And you see the disk here, which is the two hypotheses from the previous slide. This is the artist's impression of our home. This is our cosmic home. This is our Milky Way. Now, this is an artist's impression because we haven't really sent spacecraft further than just outside of our solar system, which would be the Voyager spacecrafts, which have been traveling since the 1970s. And so we don't know that it actually looks like this. This is simply an artist's idea of what it looks like. Tonight, my goal is to start filling in this picture with real data and to show you what we think the Milky Way actually looks like. One thing to note about this is that this galaxy is our Milky Way. The sun is about 2/3 of the way out, about 28,000 light years away from the center, in an orbit that takes about 230 million years. I don't know Colorado very well, but I would say the center of the galaxy is Denver. The sun would probably be here in Aspen, a quiet suburb. Maybe it's not even a suburb. I think this would be called a village. Is that right? So the sun is in a village. That's great because it takes a village to raise a child. But the sun is in an orbit about 230 million years. So it takes, the last time the Earth was in this position was right around the time the dinosaurs were walking around. And skip that. And just say, we live in this spiral galaxy. Here. The spirals are very apparent in the image. And there's a bar in the center. That bar, spirals connect to the bar. And we live in what's called a barred spiral galaxy. And one of the big questions that I have when I entered this field is, how do we know that the artist got it right? You know, art is art. It's impression. How do we know that the artist got the science right? And that's what I want to answer today. In order to answer that, I have to be able to observe a large number of stars. I have to be able to map the galaxy, kind of like the first explorers, and build a map. Now, in the early days of astronomy, building these maps were really hard. We only could take observations of 100, maybe 1,000 stars. It was a big sample back then. But today, we're moving beyond that. We can go to billions stars. And so we've entered what we call the industrial revolution in stellar astrophysics, where we're not just doing one star, 100 stars, doing billions of stars observing billions of stars at any one time. So I put onto this industrial revolution image that I got off of Google, all the different surveys that we're working with and various faces of the members of my group that are working in this industrial era. One of the biggest tools that I use is a spacecraft called Gaia, which is pictured there. And Gaia is a European Space Agency mission to produce the most precise three-dimensional map of the galaxy ever attempted by any human being ever. To do this, it is going to map something like 1 to 2 billion stars, which is still only about 1 or 2% of the galaxy. It's a really small percentage, but it's still a huge volume of stars. And I went to the UK to study for my PhD because this is a European mission and because I wanted to be a part of it. This mission cost about €1 billion. So initially, the goal was to get 1 billion stars. So it's about a euro per star. We accidentally got 2 billion stars. So 50 cents. Not too bad. And so with Gaia, the way we measure distances, we basically can measure the position of a star in the night sky. We also have to measure its distance, where it is in that 3D space in order to get our full map. And the way we do this is through a process called parallax, which I'm going to describe first, and then we're going to do a demo and see if you all can recognize how to do it. So the way we do this measurement of the distance of a star in space is we take an image, let's say we want to measure the distance to this nearby star. We take and we have these very distant background stars that are really, really far away. We take an image of it in June, and the star appears to be over here relative to that background set of objects. We take an image again 6 months later in December, and the apparent position of the star appears to move. And that relative motion is called parallax angle. That is very related to the distance. And so to give you a sense for that, it's a lot of words, but to give you a sense, I figured we would try a demo. So this is the Seven Sisters, the Pleiades. This is one of the most beautiful clusters that you can see in the night sky. Let's say if you hold out your hand like this and create a fist with your thumb up, like this. Your thumb, let's envision your thumb is the star. You want to know the distance. Now put your thumb really far away from your face, all the way out, and blink your eyes back and forth. Close one eye, blink them back and forth. You notice how the position of your thumb relative to the Pleiades changes? Do it again, but now put it really close to your face. You notice it changes a lot. That parallax. In fact, our eyes are separated, just like we take those two images on different sides of the Earth's orbit. Our eyes are separated for depth perception. If we were like a hammerhead shark, where our eyes were like this, we'd have incredibly great depth. But Gaia does exactly this. We take an image on one side of the Earth's orbit, like one eye. Take an image on the other side of the orbit, second eye. Right? And the distance to the star, if the star's position changes a lot, it's close to us. And if it changes a little, it's far away. Exactly like you just did on your own here. That's how we measure the distances and map galaxy in full 3 dimensions. The second thing we do is something called spectroscopy. Anyone know what this is? Pink Floyd, good. This is also lost on usually the Gen Z crowd, but the millennial crowd too. This is the album cover for Pink Floyd, Dark Side of the Moon. It is a white light going through a prism and breaking into the rainbow. Pink Floyd got this mostly correct. It's kind of wrong. If you pass white light, like say sunlight, through a prism, this is what you'll see. You see the full color spectrum, so Pink Floyd got that right. You also see these dark bands appear in that spectrum. Each one of those is an element on the periodic table. To someone who's trained, I can look at this and say, that right there, that's hydrogen in the atmosphere of the sun. This is magnesium in the atmosphere of the sun. This is sodium. And I can measure the size and shape of those dark bands and tell you how abundant each element is in any star night sky. So this is what I do at Donald Observatory and with the GMT when it comes online in Chile. I actually take starlight, pass it through this telescope, break it into the rainbow. We use something a little more specialized than prisms. And then I see this and I record the elemental abundances of stars in the night sky. And from these observations, what we've learned about our galaxy is that it has 5 components. So I'll walk through each component, tell you what it is, and I'll compare it to breakfast food, because it's my favorite type of food. So the first is the thin disk. The thin disk of our galaxy is incredibly thin. Thin disk. It's like a French crab at some level. That's its aspect ratio. And the sun, us, we live in the thin disk. The thin disk is mostly very young stars. For astronomy, young is like 4 billion years. Not too large. And all the stars in the thin disk are going around beautifully in these circular orbits around the galaxy, and around they go for 200 million years or more. That's the thin disk. Then we get to the thick disk, and the thick disk is like a very thicker form of the thin disk, which is like the fat American pancake that I like. The thick disk stars are going around in orbits similar to the thin disk, but they're kind of wobbling around a little bit more. But also their chemical composition is such that they're more metal poor. They don't have as much metal in them. I should mention, for astronomers, you've got hydrogen, you've got helium, you've got metal, because there isn't that much of the other stuff. The carbon that makes up our bones, the oxygen that we're breathing now, the iron in our blood, all of that is metal, an astronomer, and is created inside of stars that are in these different components. The thick disk. And in fact, my PhD advisor was one of the discoverers of the thick disk, which is also why I decided to go to the UK. We've got then the halo on the outskirts. That's that big ball, the disk, 2 components I just talked about, that's the disk. The big ball of stars in our original hypothesis, that's the halo. Now, I had a hard time finding a breakfast analogy for the halo. So what I envisioned is, let's take that thin crepe, surrounded by that American pancake, let's batter it up and deep fry it. Sounded like a great breakfast to me. Right? So that battered on the outside, that's the stellar halo encompassing the full galaxy. That is the outskirts. It is all of this. And the oldest stars live there. And so most of our archaeological studies of the galaxy happen deep inside of this halo. That's where things are getting stripped apart, torn apart, and embedded into our Milky Way. Talk a little bit more about that later. And then finally, our last component is the bulge, which is like a big ball of butter that you drop in the middle. Okay. So the bulge is mostly made of very old stars, very metal rich. We think actually some of the oldest stars in the night sky, some of the oldest stars in our galaxy and the universe probably live deep inside of the galactic bulge. I have a student, Maddie Lucy, who actually is studying that. So that was the cartoon. This is our highest quality image of the galaxy that we have to date, the Gaia spacecraft. And to drop on those different components, we've got our big ball of butter, bulge. We've got our fried batter on the outside, that's the halo. We've got our French crepe, that's the disk. And we've got our thick fat American pancake, is the thick disk. And this is how our galaxy is structured, how we think it's structured, at least in all the evidence that we have today. And my group at the University of Texas is called the Galactic Archaeology Lab. And the way that I've tried to structure my group is I basically send each grad student to a component of the galaxy and tell them to become an expert on it. Then they teach me. By the end of their PhD, they're teaching me about that particular component. So I've used a divide and conquer approach because galaxy is too big for me to try to figure out by myself, which is why we have students and postdocs. So Maddie Lucy, for example, she just finished up a couple of weeks ago. She studies the galactic bulge. She's written a large number of papers in the galactic bulge, and she's actually found some of the oldest stars that have ever been discovered in the Milky Way in the galactic bulge. I put a series of papers up to kind of give you a sense. I've got one student now working in the galactic halo, 2 more students working in the galactic disk. And one of the things about becoming a professor at I think I became a professor at 25. Now I'm 32 and my students are graduating and becoming adults, and it's great. And I'm like teary-eyed sometimes when I talk about it. So my first student, Drea Carrillo, graduated in 21. And then I had two students, Maddie, who graduated about a month ago, and Tyler, who graduated just last week. And one of my postdocs has now become a visiting assistant professor at Indiana University. So one of the best privileges of this job is that we get to train the next generation. And I always thought, that's like, when tech companies say we're here to change the world for the better, like I'm finally in a position in my career where I'm starting to see my students grow and thrive. And that to me is one of the most exciting things about my job. And I also work with like 15, 20 undergraduate students as well, who I couldn't picture here because the slide is not large. Okay, so this is our galaxy. This is our spiral galaxy. I want to go back to something I had showed you earlier. This is in profile. What if we go to that top-down view? Right, so this is our galaxy, the top-down view of the spiral arms and the artist's impression. And so one of the questions I had was, did the artist do a good job here? What does the science say about these arms, about this structure? Because our question we asked at the beginning was, how is the galaxy structured? So this leads me to 2017. I just finished my PhD. And I went to the Flatiron Institute in New York, sponsored by the Simons Foundation. And I remember witnessing a debate between two very prominent people in our field. There was David Spergel, who has been here many times to Aspen, who I remember looking at the Gaia data, and we were all thinking, what can we learn from the Gaia data? What can we learn at all? And David Spergel said, we should be able to see the spiral arms. And another guy, David Hogg, two Davids, is what we called him. David Hogg said, no, there's no spiral arms in the Milky Way. It was just a provocative statement. I don't think he actually meant it. I think he was just trying to play contrarian, which is classic for David Hogg. He's a really wonderful scientist because of that, I think. So I watched this exchange when I was a postdoc. I thought to myself, Gaia should be able to answer that question. Does the Milky Way have spiral arms or not? That was the question that I had to ask myself. Are there spiral arms or are there not spiral arms in the Milky Way? And more importantly, did the artist get it right? That's our question. Our hypothesis, I have to go back into the literature and read what people have read or what people have written about this topic. The first real instances of spiral arms coming up in astronomy was in the 1950s. 1952, there was this paper. I don't know if there are any astronomers in the room. This is obviously not what our papers look like today. They're much longer with figures. This was a simple little, like 2 paragraphs. This was a paper back in the 1950s where they actually used the Yerkes refractor to measure the positions of very young stars in the night sky and see if there were spiral arms. If you look at this paper, and the paper after it in 1953, this was the image that they posted in the paper that was the first evidence for spiral arms. There's 2 hypotheses here. Hypothesis 1 is they're spiral arms. Hypothesis 2 is that they're not. By a show of hands, how many people think that these black points represent spiral arms? No one's convinced. Very few people are convinced. And I asked somebody in the audience, why aren't you convinced that that's a spiral arm?
Not a big enough sample.
Not a big enough sample. Right? This is about as good as we could do in the 1950s. We're in a completely different era now. We're in the industrial era. So we thought, why not check this now and see what it's like? Let's bump this from, say, tens of stars. Let's use 1 million stars or 1 billion and see if we can see something. That's what we did. That's what various astronomers did. So this is what they claimed were spiral arms. This was state of the art in the 1950s, and this progressed. And we believe that image that you saw was based on this data. And this data actually was expanded to 1,000 stars. And that's really what the image is based on. If you expand it to 1 million stars, Our next step of the scientific method, we created a hypothesis. There were spirals. Most people are unconvinced. Some people were convinced. Let's re-observe this with Gaia. Let's use 1,000,000 stars. This is what it looks like with 1,000,000 stars. 1,000,000 young OB stars from Alois Poggio's. This is the sun in the center here. This is one of the only plots. I only have 2 plots in this. This is the sun at 0, 0. This is 13,000 light years out away from the sun towards the galactic center. This is 13,000 light years away. This is, of course, the galactic anti-center. And then this is also 13,000 light years from. So with 1,000,000 stars, let me ask the audience again, how many people think that the Milky Way has spiral arms? Turns out, this is an arm, this is an arm, this is an arm. So the red is where there are large numbers of stars, and the blue is where there are not that many. So if the red is where there's a large number of stars, that means that a large number of stars are making up that spiral arm, and there's an inner arm region, there are not that many stars. And there's a large number of stars again, where the spiral arm exists, and not that many. And then there's a larger number of stars, and not that many. Those are the spiral arms. So let me ask you again, how many people think that the Milky Way has spiral arms? The people not raising your hand, we should talk afterwards, because I want to know what we convince you. So this was some of the key evidence for spiral arms in the Milky Way. And my group took it one step further. We actually asked, is there something in the chemistry of the stars that tell us the spirals exist? And this is the second plot, last plot I will show you in this, the exact same plot as before, but now we're coloring by the metal excess, which is how much metal is in the star. Red means there's a lot of metal. Blue means there's not as much metal. So wherever there's a spiral arm is the black line here. This is a spiral arm from previous slide. The black line is another spiral arm from the previous slide, and this is the last spiral. One of the coolest things that we were able to do this year, actually this came out earlier this year, that we were able to show that not only do you see the spiral arms in the spatial positions and the positions of the star, but wherever there's a spiral arm, stars are more metal enhanced. It's redder. Wherever there's a spiral arm, it's red. Wherever there's not a spiral, it's blue. So the stars in the spiral arms have more metals in them than the stars that are not in the spiral arm. That was even stronger evidence for the fact that we have spiral arms in our galaxy. And again, these are the spiral arms here. One Aquarius arm, local arm that Arc is a part of, Sagittarius arm as well. And this was great because it actually came out in a press release last week. We read the press, astronomy. There was this image of this is that image of the Milky Way, that artist's impression. And on top of it, we've put these spiral arms of our galaxy. And the image that the metallicities of the stars were, again, these are metal rich in the arm, metal poor off the arm, metal rich in the arm, metal poor off the arm, and metal rich in the arm. Okay, so this came out just last week, showing that chemical cartography or chemical mapping of the galaxy allows us to see the spiral arms for the first time. So this artist's impression is bad, actually, surprising. It's pretty good. Okay, so this is some of the work that we just did. Well, if we go back to that original spiral arm debate, I said earlier, it's Virgo saying there's spiral arms, and David Hogg contrarily saying, no, there's not, just to be a contrarian. We could probably say spiral arms probably exist in the Milky Way. And I hope I at least somewhat convinced you that spiral arms are there, embedded in the Milky Way. There's a lot of literature on this, and I've posted some of it here in case you're one of those people that really wants to go and read the literature afterwards. All right, so I only have a couple more minutes. I think I have 5 minutes. Yes. So we're going to end with one last question. We're going to walk through the scientific method again. The last question is, how does galaxies in the universe form? Obviously, I can't answer that question in 5 minutes, but I'm going to try. And so how are galaxies formed? I'm going to start not with the science, but with a mythological story. The reason why I'm starting there is because when I went to Ghana, I actually did ethnoastronomy. I combined ethnography and astrophysics to understand how West African cultures see and view our cosmos. And so I think that bringing the human element to the skies is an important aspect. And this is the story that I recounted actually when I gave the commencement address at my alma mater. I went back to Ohio University, give the university-wide commencement address a couple of years ago, and this is the story that I told. So if you are from the Cherokee tradition, you were asked this question: how does the Milky Way form? The answer starts in a small village with a mom and a pop. They were responsible for milling corn, the corn meal for the winter. We don't really have winters in Austin, so this doesn't work very well. We have winters here in Colorado. They're responsible for milling corn into cornmeal for the winter. When they went to the shed where they were storing the cornmeal, they found out that somebody was coming in and stealing it. They looked at the tracks of the perpetrator, and it turned out it was a dog. They looked at the tracks, and it was big paw prints that were too big to be a regular dog. It was a spirit dog. And so the townsfolk decided, we need to scare this thing out of our village so that we have our cornmeal. And so they all waited up one night, banged their loud noisemakers when the spirit dog dug its teeth into the cornmeal. And the spirit dog actually got scared. That's why it says sometimes it takes a village, because it took the whole village banging their noisemakers to scare this spirit dog into the sky. And when it went into the sky, it had some cornmeal with it. That drops of cornmeal became the Milky Way. That is the mythological story in Cherokee tradition. I don't have time to talk about the Greek tradition, but it has to do with Hercules. I love that story. So if you're finding me afterwards, I can tell you. That's a Cherokee tradition. But the way we think galaxies actually formed is through a process called monolithic collapse, where you take a big gas cloud, you let it collapse due to gravity, and you get a big ball of stars. You get a disk of galaxies by taking that big ball of stars, you give it a little bit of spin at the beginning, kind of like an ice skater. When the ice skater kind of closes their arms and spins up, you spin it up into a disk. So it's a similar process as a ball of dough, right? Pizza. That was one idea. The second idea was you take galaxies and you collide them together. You allow one galaxy to cannibalize other ones. That creates a new set of galaxies. That was the second idea. The way we think galaxies actually form is through both of these processes, and I'll just show you a simulation quickly, where you actually see, the simulation is going a little slow, you see these little proto-galaxies that are forming. This is an actual simulation of stars from the Latte simulation. Those stars, galaxies are forming, these are called proto-galaxies. These formed by that big gas cloud collapsing, your big ball of stars. And then the galaxy in the middle is going to go in and gobble up, cannibalize all the little things nearby. That galactic cannibalism is likely what creates galaxies like the Milky Way. In fact, you look at observations of the Milky Way, simulations of these cannibalism, galactic cannibalism. You look at the Milky Way's halo, you actually see streams of stars that are being stretched and pulled apart as the Milky Way is cannibalizing them and building them into our Milky Way. So the theory was you should see cannibalistic effects. You should see things getting stripped and shredded apart. And in fact, if you look at the real observations, you see these little streams. Like there's a little cluster of stars there, right here. Hold, I can't go to the middle, so I'm going to try to point here. So I'm going to do this. This is a ball of stars, and it's getting shredded apart in the Milky Way. We can actually see this in real time. So that is how we think galaxies form. They first start by these big balls of gas that collapse, create your ball of stars, and then they cannibalize everything around them. That's how we think the Milky Way created. Answer your question in 1 second. I just want to say that I'm very lucky to have had worked with very many students and postdocs, have funding from various sources that have allowed me to publish many papers on trying to understand and unlock the secrets of our galaxy. And I want to, I can just leave up the summary afterwards. I want to leave you here with this image of the Milky Way here in Aspen. I really encourage you to go out tonight, if it's not cloudy, see the Milky Way for all of its glory and beauty here in Aspen. You can see it in the town. And hopefully you'll look at the Milky Way with a completely new view, knowing now its structure, its disks, its spiral arms, and its formation, symbolism, in terms of its process of formation. And so that probably tells me I should probably finish. So thank you very much for listening. So any questions? I see a question there.
Any kind of animation you could show at any scale or any time scale or distance scale, so we can see how things might be moving over?
Yes, this is the best animation that I have to date for this. This is the latte simulation due to Andrew Wetzel. So this is actually showing you, this is not unastronomerized, so to speak. So this is a scale of 100 kiloparsecs. That's 100,000 times 3, like 300,000 light years. That little bar is 300,000 light years. And what you're seeing is actually an animation of how galaxies are building themselves. This is going to become, by the end of this simulation, this is going to be a single galaxy. It's eaten up every other little galaxy in its neighborhood. And the Milky Way is currently doing that right now. We know that because we can see it. I should also mention, not the biggest galaxy out there, the bigger galaxy called Andromeda that's headed our way, and it will cannibalize us in a few billion years. So our galaxy will be cannibalized by another one in the process of building a new galaxy that will be a merger of Andromeda and our galaxy. So we won't always look like we look. Let's go there, then there.
Is there a star stream that's easy to see in a small telescope?
That is a good question. Is there a small stream we can see through a telescope, a small, like an amateur telescope?
How 8 inches?
I think that it would be quite difficult to see any one of the streams that I showed. You probably need a telescope about 1 meter size or 2 meters in size. There are some telescopes out there that the public can use to see this. So for example, McDonald Observatory once every month opens up our research class telescopes and we put an eyepiece on it. It's the biggest.
In there.
It's great, isn't it? So if you ever get a chance to go back, I don't know if you were at a special viewing night, is what they're called. But if you ever go to a special viewing night, we actually interrupt research time for the public. And we put an eyepiece. It is one of the only large telescopes in the world. We literally put an eyepiece on it. You can see, and that might be one telescope you can see it in. Yes.
Black holes. What do we know about black holes?
We know quite a lot about, well, we know quite a lot, nothing at all about black holes in our galaxy. We know that we have a central black hole, a supermassive black hole at our galactic center. And that's going to be in the bulge, in the big ball of butter that I talked about. And that black hole, we know it because there's stars zooming around it. And that was actually a Nobel Prize. Andrea Ghez, I think she gave a public lecture here a couple of years ago, and a member of the center. She's actually one of the few discoverers of that. So that's the supermassive black hole that we have in the galactic center. We also know of stellar mass black holes. So there's a black hole about the size of the sun, probably actually like 10, 30 times the mass of the sun. And actually, many people in this workshop are actually trying to find those particular black holes. So those are harder to find. The dormant ones, especially because they're not eating up anything. They don't really radiate, so it's hard to find them. But that's why I say we know some and nothing else. Yes.
This is probably a really stupid question, but why, when we can see the Milky Way, I see it here when we're here. Why does it always feel like we're not part of it, like it's some separate entity from us?
A good question. So 2 things. One, as I tell my students, there are no stupid questions. And I tell them that in large part, and I also, there's 2 things I want to say to this. 1, there are no stupid questions. 2, it's okay to be wrong. In fact, science is about being wrong, not falsifying. So I say that in groups of people because I want you to know it's okay to raise your hand and ask a question that may sound stupid. So the question itself is, why does it feel like we're not necessarily a part of the Milky Way, even though we see it? Good rephrase.
Yeah.
So I would say that one of the biggest challenges of the Milky Way is that we're inside of it. We have a skewed perspective of it. It's kind of like Aspen, right? How many people would know exactly what the street map of Aspen looks like right now? A couple people. Right? I don't know what it is like. But if I go and hike up, I think I recently hiked Hunter Creek. You can actually see Aspen. And from that top-down perspective, then I have a better perspective of it. So what I would say to that is probably that because we're inside of the Milky Way, it kind of feels like we're not really a part of it because we don't see it in the same way that I showed it in the simulation. If we were above it, then we would see it in all of its full glory, and then it would feel more majestic. So to speak. Maybe that would be why, but I'm honestly not sure.
Why doesn't it look like there are stars all around us instead of looking in the sky and seeing that swath of cloud dust in Milky Way?
You can see the Milky Way itself.
Yeah.
You can see stars all around. And the reason why you can see stars all around is because we're embedded inside of it. We're literally in the galaxy. And so there are stars in all parts, all around us, all the time. Now, if Earth was way above here and the galaxy is right here, then we would just see the top-down projection. Right? So it's a projection. I would say. If you have further questions.
One more
then-
question. And then
One more question. I'm going to go to the way back because we haven't gone all towards it.
The telescopes that have been sent out, like the Webb, and how do those affect your research? Where they headed? Think about it.
Yeah, so how about space telescopes? How do they affect my research and where are they going? So Gaia, which is the spacecraft that I primarily use, the European Space Agency mission, is actually at the same location that James Webb Space Telescope is. It's in Lagrange point 2. And they actually will stay out in L2, just sitting there orbiting around the sun and the Earth. And for those telescopes, one of the most beneficial aspects of getting to space is that you can get rid of the atmosphere. The atmosphere is great for humans because we kind of need it to breathe, but it's actually really bad for astronomers because it creates twinkling for the stars. The stars twinkle, so it's actually good for, I guess, both breathing and for storybooks. But effectively, right, the light goes through the Earth's atmosphere jitters it around, so the stars appear to twinkle. But that means it's hard for us to get a good image of the star. So James Webb and Gaia really are transformative at some level because they allow us to get outside of the Earth's atmosphere, allow us to take very precise and clear images we otherwise wouldn't get. And so Gaia allows us, for example, to get really precise images where we can track the precise position of a star. Whereas here, a star would be wobbling around. That's why they affect my research. In terms of where they're going, Gaia's nominal 10-year mission is up now. So they'll have one more data release. James Webb, just getting started. So we're just getting started on that date.
we have to stop the formal part here, although I understand that Keith will stick around for a few more minutes. People have questions if they want to come up afterwards. I just want to take this opportunity to once again thank Mr. Hawkins for one of the talks. And of course, a big thanks to all of you for coming, and hope to see you here again in the coming weeks. Thank you.